minus 3, essentially, right?
Yeah.
Which means, right?
Oh, you can just say minus root 3 and root 3 over 2.
Right.
Because minus 1/2 and 1/2
Yeah,
is already in.
I'm making this, I didn't need to do this calculation. I'm an idiot. Like, it's fairly obvious that if you look,
because you can just pull up the 1/2. Ha.
like, if you, well, I'm just saying, let me say it this way. If you look at q, I join the cube root of 2 and the I root 3, right?
Yeah.
Which, of course, we could write as a square root of minus 3. If we look at that, we can build alpha 1 and alpha 2 from these two things. This is the thing. It's like, it's a cube root of 2 times, and then, see, and then we have a half that's already in q, minus a half is in q, right? And then a half of the square root of minus 3 is something that we'll definitely have in this space.
Yeah.
So this contains all three roots, right?
Yes.
So this splits x cubed minus 2. This is the splitting field. And the picture here is a little bit different, right? So like, we had this one. Well, on the one hand, you've got that over q adjoin the square root of minus 3, right?
Mm-hmm.
But on the other hand, you can go to q adjoin alpha 1, q adjoin alpha 2, q adjoin alpha 3, right?
Yeah.
So, which is me just saying those are other proper subfields of the splitting field.
So that would make this
and
3.
Well, that's the question, right? Yeah.
What is it?
These are all degree 3 extensions because the cube root of 2 is, I mean, q adjoin the cube root of 2, right?
Mm-hmm.
This over q is 3, right? We've worked this out before. Because x cubed minus 2 is irreducible polynomial over q, which takes the cube root of 2 as 0. And
but the root minus 3.
yeah, this is the degree 2, right?
So that means that would have to be degree 6.
Yeah, this has to be degree 3.
Yeah, and
These have to be degree 2 extensions, yeah. And indeed, that is a degree 6. So the splitting field of x cubed minus 2 is a degree 6, which is 3 factorial extension over q. All right. X to the 4, example 4, I had a really cool calculation, which I have left at home. I want to show you how we can do example 4 using complex. So while I'm adjusting the camera, we're trying to understand x to the 4th plus 4, I believe. All right, we're trying to understand what's its splitting field, yeah? And so my point to you is, okay, well, we're working with a rational polynomial and so we know that in the algebraic closure of the rational numbers, the complex numbers, this will split. So we can use complex calculations to understand this if we want. And so really what we're trying to solve is this, right? X to the 4th equal to minus 4. So that means x is, well, let me call it alpha rather than x. Alpha to the 4th equals minus 4. So alpha should be an element of the 4th roots of minus 4. What are those? In terms of our complex analysis calculational
Um,
schemes.
to the I pi 8 with alternating i's. Oh, with the 4 out front too, though.
Yeah.
Okay, so 4 e to the I pi 8.
So here's the way I would write this. I would say it's the principal fourth root of minus 4, right? And then you take that and you multiply by omega 4, right? Omega 4 is I. So you got yourself a 1, an I, a minus 1, and a minus I. This times that gives me the 4 solutions. Now the minus 4 is equal to 4 e to the I pi, right? So the fourth root of 4, by the way, is the square root of 2. And so what we're actually looking at here is the square root of 2, e to the I pi over 4. So that's the fourth root of minus 4, right? The principal fourth root. And then times 1i minus 1 and minus I. And so what is that? Well, that's square root of 2 times 1 over root 2 plus I times 1 over root 2, right? And the square root 2's cancel, and you're left with 1 plus I times the fourth roots of unity. So what you got in summary? You got 1 plus I, or I minus 1, or minus 1 minus I, or minus I plus 1. In summary, what you've got is plus or minus 1 plus or minus I. You got these, those are your 4 roots. Now, in Dummett and Foote, he has a connivingly tricky way of deriving this. But this is, right, I'm just showing you sort of clunky, standard, complex analysis, fourth roots of unity way to derive this. And so what we have is x to the fourth plus 4 is equal to, you know, what we're really looking at is x minus 1 squared plus 1 times x plus 1 squared plus 1. Because that's what comes from the conjugate pair of zeros, 1 plus or minus I, or minus 1 plus or minus I. Right. And like he derives that factoring through sneaky arguments, just algebraic, just hubris, really. The question though is, what's the splitting field?
Well, no, you can just have 1 and I. You can get, would it just be I? Q to I? Oh, wait.
Q,
Yeah, I think so.
Q adjoin I think will do it because,
I will get you negative minus I, because it's I cubed.
right, from I we can get 1 plus I, we can get
1.
1 minus I, we can get minus 1 plus I, we can get all our roots. They're all in there, absolutely. So this one has a splitting field of degree 2 over Q. So we saw earlier a fourth order polynomial which needed a biquadratic extension, a degree 4 extension to split it. Here's a quartic which has a degree 2 extension which splits it. You know.
So they're unique up to the polynomial.
Yeah, I mean, and you know, just don't forget, you can have something like this, right? X to the fourth minus 1 in, C. I mean, this is very silly, but it's already split in C is the thing. See, this is x plus 1, x minus 1, x plus I, x minus I. So it's already split in C. So C, it's, yeah. No. So these are good examples. We should talk about the cycloatomic fields. Cycloatomic fields here. So this is on page 539. So his notation is, actually I'm kind of skipping. I'll skip over here to 540. Zeta n, I'll eventually write it, is equal to e to the 2 pi I over n, right? And so zeta n to the k power is equal to e to the 2 pi I over n, to the k power, right? And these are principal, well, not principal, these are just nth roots. Nth roots of unity. And this is the principal nth root of unity. He gives a more general definition of principal nth root of unity, I believe, on the previous page, which basically says any generator of the cyclic group of all nth roots of unity is called a primitive nth root of unity. So basically, you can take any relatively prime power of zeta n, and it will also give you a principal nth root of unity. In the sense, it'll generate all the others. So the way this works, of course, is you've got one, and you look at the unit circle, right? And if this is like zeta 1, then like zeta 2 maybe, zeta 3, if I did it right. I didn't do it right, but I'm an idiot. Zeta 1 squared, zeta 1 cubed, zeta 1 to the 4th power, zeta 1 to the 5th power, zeta 1, my zeta is degenerating, zeta 6th power, zeta, oh man, it's getting worse, zeta 7th power, and apparently I'm drawing a picture. Oh man, it's getting worse with every zeta. Oh, see, now I regret drawing 1. What should I have been writing? 8, 8, 8, 8, 8, 8, 8, 8. The 8th power of zeta 8 is just 1 again. So these are the principal 8th roots of unity. And he's got the formula for it, actually. The 8th root of unity is the square root of 2 over 2 plus I times square root of 2 over 2. Of course, that's the e to the 2 pi I over 8, which we just were calculating a second ago, e to the I pi over 4. So it should be a little bit familiar. So those are principal 8th roots of unity. All right. And so here's, for example, right, there's other ones, but what's the principal 4th root of unity? Principal 4th root of unity was e to the 2 pi I over 4, right? Which is e to the pi I over 2, which is I. So this is called the cycloatomic field of nth roots of unity. So we already had one of these on the board, right? Q adjoin I is the cycloatomic field of fourth roots of unity. Yeah. And he says, now he gives an interesting discussion. So determining the degree of this extension requires some analysis of the minimal polynomial of zeta n over q. All right? So what's the minimal polynomial of zeta sub n? How should we attack that problem?
Well, depending on our choice of I, we just keep splitting it into smaller fields, right?
I mean, yeah, we want to find the smallest field that works. That's true.
No, but what I'm saying is, like, can you keep, like, can you do to the 16th root of unity and then the 32nd, you know? Or, like, do these start to overlap at some point?
Oh, how are they related?
Yeah.
I don't know right offhand. They are related.
Yeah.
For example, the sixth roots and the third roots are very related. Like the square of the sixth root is the third root. So certainly that says that the cycloatomic field over zeta 6 is going to contain the cycloatomic field of zeta 3, since zeta 6 squared gives you zeta 3, for example. They are related in that sense, but maybe not in others. It depends. It's complicated, actually, I think. But this we can figure out, see, because we're looking for the polynomial of least degree, which takes zeta n as a 0, right? But remember where this came from. This came from solving the equation x to the n equal to 1, right? For x complex.
Yeah.
Maybe z to the n equal to 1, if you like. So we already know that zeta n's a 0 of this, right?
Yeah.
In other words, if we look at x to the n minus 1, we know that that has this as a 0. But we also know that this factors. Maybe we didn't know that, but let's know it now. So what's this? X to the n minus 1 plus x to the n minus 2 plus da-da-da-da plus x plus 1, right? I mean, work it out if you don't believe me. When you distribute this through, you get an x to the n.
Yeah, and it kills the other term, too.
All the way up to x.
It kills the middles.
And then when you subtract minus 1 times this, you kill the n minus 1 all the way to killing the x, and then you're left with a minus 1. So there it is. Now, this has a name.
We need a plus 1 on this side. Minus 1 times 1. Minus 1.
Yeah. I mean, minus 1 times plus 1.
Yeah. Right.
It's okay. It's all good. Now, I mean, this is generally true, but it's more interesting when p is prime, okay? So
N is prime.
when p is prime, so consider n equal to p prime, right? Same math we just did, all right? And this has a name, phi p of x is equal to x to the n minus 1, well, in this case, x to the p minus 1 over x minus 1, which is just a kind of sneaky shorthand for this over here, you know? I'm an idiot, x to the p minus 1 versus x to the p minus 1. See, this and that sound the same in English, but they're very different. So plus. So this is the so-called, what is this called? This is the so-called, I think it's called the Psychoatomic Polynomial in the number theory book. And we have shown, actually, that was irreducible last semester.
Yes.
We did, for prime p.
Yeah.
So, irreducible, what's that mean? That means we found an irreducible polynomial, a monic irreducible polynomial, which takes the nth root of unity, the pth root of unity in this case, as its 0. Therefore, that means that Q extended by the pth root of unity is degree what over Q? It's the degree of the cycloatomic polynomial over, right, which is p minus 1. It's important that p is prime. This breaks down when p isn't prime. Q adjoin I, right? Q adjoin I is Q adjoin the fourth root of unity.
Yeah.
It is degree 2,
Yeah.
not degree 3 over Q. And this one, how about Q adjoin the eighth root?
Built it from.
I mean, this is, so it's this is it, right?
Yeah.
So it looks to me like you need, I think you need an I and a root 2 for this one. So, and those are oil and water, right? There's no way to get one from the other.
Yeah.
So I believe this is degree 4. Like I think Q adjoin I think the cycloatomic field of order rate is degree 4 over Q. And then our final example for today, if I have time. I do. Woohoo! Oh man, I thought I wasn't gonna make it. I thought I was gonna have like one example left over, you know? The next section is the one I've got to be really careful with because there's a lot of material in the next section we don't need. So my goal in this course is for us to focus mostly on characteristic 0. So I will dabble a little bit next time in the characteristic P material, but I must be careful not to say all of it because the totality of it, it's quite something. But anyway, I'll try to state results, but just not do the proofs of the characteristic P thing. I think it's important to do some of them because there's some really neat things in there. Like there's the freshman's dream is true over characteristic P. Yeah, like A plus B to the P power is equal to A to the P plus B to the P. This is true over characteristic P. Anyway, so here's the example. We have x to the P minus 2. All right. Let's talk about the splitting field of this guy. So, what are you trying to solve? Really, you're trying to xp equals to 2, right? Right, and I'll put an alpha here just to, you know. So alpha is an element of the pth roots of 2, right? Which is the pth root, ordinary garden variety pth root of 2 times what? Times 1 zeta p squared zeta p to the p minus 1. These are the pth roots of unity. Those are the, so basically your x to the p minus 2 splits as x minus the pth root of 2, right, times x minus zeta p times the pth root of 2, x minus zeta p to the p minus 1 times the pth root of 2. There you go. That's how it splits. So the splitting field needs to have, let me call these things, you know, alpha 1 through alpha p, right? So I think we want Q adjoin, well, definitely we're going to need the pth root of 2, right? And I believe if we throw the pth root of unity in there, that ought to do it. See, because we can build all the other roots from those two things. And so the question is, what degree is this? See here, so here's the picture he draws. He's like, okay, so this has a proper subfield of Q adjoin the pth root of unity. This, of course, also has a proper subfield of Q adjoin the pth root of 2. right? These are both over Q. So the degree of zeta p over Q is p minus 1. We just worked that out. The degree of this over Q is p, because remember x to the p minus 2 is irreducible by,
So p squared minus p.
right, well, what goes up at the top there then? I mean, it has to be a number which,
Wouldn't, if you extended z by p through, you'd get p, because that and q are p.
yeah, I'm not sure quite the logic. Maybe you can tell it to me.
I think, what would it be?
Well, the thing is, this has to be p minus 1,
Yeah. Oh.
and this has to be p, because otherwise,
I mean, remember that old theorem of the splitting field?
uh-huh.
Degrees? You get that immediately. That's the only way I can think about it. So yeah, do the whole thing over q, and that has to equal to q.
Oh, right. I see what you're saying. It has to, on the one hand, it has to be q p root of. So I'm missing something here, right?
Yeah, that's it.
The zeta.
So that's equal
This
to that.
over. Sorry. Q. I'll get it eventually here. I should have come up with a name for this thing, so I need to keep drawing it down. Yeah. Over q adjoin p through to 2.
And then p through 2.
Good grief. Oh, man. All of a sudden, it's getting to me.
Yeah.
But on the other hand, it's also,
Yeah, the other way. But what you get is p minus 1 p, and then the other side p minus 1 p, so you get like p squared minus p. That's the degree.
yeah, and so why can we conclude that about the, why is these factorizations, where are we using that p is prime in order to make this, I mean, I agree with you. So this has to be the product of this times that, and that times this, right?
Yeah. Well, we know dp, and we don't know that. Oh, okay. I can do this. So
This, I mean,
qp.
so these we know for basic reasons that this is p minus 1, right?
Yeah.
And this is p.
Yeah.
So this has to have factors,
Yeah.
p and p minus 1.
Mm-hmm. But you can tell if those two are equal, that means you have to have a p minus 1 somewhere in the other one. Like, how do you get p minus 1? And how do you get p on the other one?
I mean, certainly p and p minus 1 are relatively prime, right? Like,
Yeah.
because p is prime. So, I mean, he has the,
There's an argument here to where, like, you could say, I'm just going to p through of 2 and zeta, and over q p through of 2, it can only be, it can be less, it has to be greater than, or it has to be less than p. And then the other one, you can say that has to be greater than, yeah. And you can say that one has to be greater than p minus 1. Q adjoin, okay, I'm going to call it gamma.
oh, you want to give these names? Let's call this, I mean, use really different letters, like how about, how about A? Want to use like A and B? So you've got, what do you say? You got B times P is equal to A times P minus 1, right?
Yeah. And then A p minus 1 is equal to, yeah. And so you get AP minus p minus 1, take out the p, and then you get, no, wait, what am I saying? Okay. A, take out all the sides, you
So I think it follows from like prime factorization, right?
Yeah.
Remember that if we have p is prime,
Yeah.
then there has to be a, you can write this number as a product of primes, right?
Yeah.
But p minus 1 does not contain p
Yeah.
in its prime factorization, right? Because they're relative to prime.
Yeah.
So that means p has to divide a.
The only way that can happen because it's prime is if it's a multiple of it.
Right, p, yeah, a has to be a multiple of p, and b has to be a multiple of p minus 1. But on the other hand, you know that it's equal to, let's see here, so, but they have to be, they can't be multiples because these are equal,
Yeah.
right? Like, or they have to be the same multiple? I don't know, but in any event, long story short, we found is that the degree of this is p times p minus 1, right?
I used this argument in one of the homeworks, that's why.
Yeah, I do think there's like there's some small gap in what I just said, but anyway, that's
for number 2, when you're trying to prove degree, when you're trying to prove r plus a plus bi is equal to c, you can show that no matter which way you flip it, you can only get 2. But like then again, we didn't know the degree up top first, which in this case we don't know the degree offhand.
but I guess the question is, do we? I think we might, because the degree of, well, the degree of this, though, it has to be, by the degree formula,
Yeah.
the product of, oh, but then the issue is I don't, all right, well, I know that this has,
Wait. If those two are relatively prime, right?
Yeah.
That number, its factorization can't be anything else.
yes, it has to, I mean, I think essentially p and p minus 1 being relative prime, this equation forces b to be equal to p minus 1 and a to equal to p.
Yeah. I think that.
At which point, this has degree p times p, yeah, p squared minus p. Yeah. So anyway, this is also an interesting example.
Yeah. Maybe someone on YouTube will.
Someone on the YouTube. So that brings us to the differentiability stuff, the separable section, which we will. Hopefully, we should finish 3.5 and 3.6 on Monday, which I think might be. Feeling better?
Yes. I was like, oh, I know what you're saying.
Yeah.
I think that's just complex, or not complex.
Well, the trouble is he cuts some things very finely, and then I have a bunch of calculations on that one.
Yeah.
I even have a way to derive it from a product. Here's how it splits.
Yeah. Okay. This is the one we're working on?
That's the one that I'm trying to prove this is irreducible,
Yeah.
but
Yeah.
there's something
That'd be a really slick way to do it.
I'm missing some secret sauce in that problem. I'm not sure what
Don't worry.
what it is.
I think my dream had a stroke of genius.
Run like the wind.
Yes. I must, because I have no idea how my watch is sharp.
Uh-oh. Have fun.
Okay, it's sharp as fast.
Have a good weekend.
Yeah, I mean, what's gonna be doing? I still need to catch up on the, I wanted like problem 17 or something, like 17 done. So I can do like 13.
I may get what's the word? Energetic and make a video for complex this weekend, so we're caught up.